Do you see the slides? Okay, so well, this starts with a result of Champier-Serre, which says that every action of a finite group on a tree has a fixed point. Serre's result is in fact more general. So a natural question is if we can extend this result to a dimension greater than 1. So there is an action of the group A5 without fixed points on the 2 skeleton of the Poincaré homology 3 sphere, which is an acyclic 2 complex. So we cannot replace a 3 by a cyclic n complex if n is greater or equal than 2. And moreover, taking the join of this space here, xp, with a free orbit for the group A5, we obtain a contractible 3 complex with an action of A5 without fixed points. So we cannot replace 3 by contractible n complex if n is at least 3. So what is left open from this attempt to generalize this is the following question, which is if every action of a finite group G on a finite and contractible 2 complex has a fixed point. This was conjectured by Casacuberta and Dix without the finiteness hypothesis on the 2 complex, and was posed in the form of a question by Aschbacher and Segev independently. So what was known about this question is the following. First, in the paper by Casacuberta and Dix, they proved that the conjecture holds for a solvable group. Independently, Segev proved the same result, that the conjecture holds for a solvable group, and moreover, he proved that it holds for the alternating group An if n is greater or equal than 6. Later, Aschbacher and Segev proved that many groups cannot act without fixed points on a finite and a cyclic 2 complex. Here, many groups means that if some finite simple groups do not appear among the composition factors of the group G, then there is a fixed point. In this result, they, of course, used the classification of the finite simple groups. And then Bob Oliver and Yoav Segev gave the complete classification of the groups G, which act without fixed points on an acyclic 2 complex. This result requires a lot of work and builds upon this result here. So the classification of the finite simple groups is used here also. So what we were able to prove very, very recently is the following result, which says that every action of a finite group G on a finite and contractible 2 complex has a fixed point. And to prove this, what we do, in fact, is proving the following. If G is a finite group and X is a 2-dimensional fixed point free finite and acyclic G complex, then there is a non-trivial representation of the fundamental group of X on a unitary group. So this proof builds on the classification by Oliver and Segev and appears across the following articles. In this first article, we do some reductions using the classification, which reduce the proof of this to proving this for each of the groups in this classification by Oliver and Segev. And moreover, in a really computational way, we prove something for the group A5, which gives this result in the case of A5. But the proof was rather computational. And then in this second paper, we extend the method used in the case of A5 in a more general way to deal with most of the groups in the classification of Oliver and Segev. And then finally, in this third paper, which is a joint work with Kevin Peterman, we address the remaining groups with a modification of the method used here. So now I will tell you a sketch of the proof of this result. So first, we need the classification by Oliver and Segev. So the classification has 2 parts. The first is theorem A, which says that for any finite group G, there is an essential and fixed point free 2-dimensional finite acyclic G complex if and only if G is one of the following simple groups. These are some linear groups over certain finite fields and the Suzuki groups. And then the second part is theorem B, which says that if we start with any action of a finite group G on a two-dimensional acyclic G complex X, then we can consider the subgroup N, which is generated by all normal subgroups N prime, which fix something. And then the fixed points by N is an acyclic subcomplex, and the action of the quotient by N on these fixed points is an essential action. So we start with any action, we obtain an essential action. This group here by theorem A must be one of those groups here. So I didn't say what essential means, just for completeness. A G complex is essential if there is no normal subgroup with the following property. For each subgroup H of G, this inclusion is an isomorphism on integral homology. But it really doesn't matter what essential means. So now with this classification, we can see the first reduction. So in this reduction, we use the Gerstenhaber-Rothaus theorem. So I will recall some definitions on equations over groups. An equation over a group G is a word here in this free product of G with the free group on our generators, which are the indeterminates of this equation. And the Gerstenhaber-Rothaus theorem says that an independent system of R equations in R indeterminates with coefficients in a compact and connected Lie group G has a solution in G. So a system is simply R equations, and a system is said to be independent if certain matrix has non-zero determinant. This matrix has at the place, at the I row and j column, it has the total exponent of the generator xj on the ith equation. So it is very natural. It's like Abelianizing this system and taking the determinant. So if the system is independent, we can find a solution in this Lie group G. And finding a solution simply means that we can find the elements of this Lie group G such that when we evaluate these words on those elements, we obtain the trivial element of the group. So this notion makes a lot of sense. And well, using this result, we can prove the first reduction, which is the following. To prove this main theorem, it is enough to prove it for each of the groups in the classification by Oliver and Seger. So we start with any action of a finite group G on a two-dimensional acyclic complex without fixed points. Then we consider the group N as in theorem B, so that the action of this quotient on Y is essential, and then this quotient must be one of those simple groups. And now, since we assume that the theorem holds for each of these groups, then we can produce a non-trivial representation of the fundamental group of Y on a unitary group. Well, now we can write the fundamental group of X as follows. Here, this number R is the same as this number R here because both X and Y are acyclic. And this system is independent. In fact, it has determinant 1 because X is acyclic. And then by the Gerstenhaber-Rothaus theorem, we obtain a non-trivial representation of the fundamental group of X on a unitary group. This extends the representation that we had on Y in some way because we have it defined here, and the solution allows to define this here. So now, for the second reduction, I need to explain in more detail the examples constructed by Oliver and Seger. So there are 3 sets of examples. The first set is the following. It is for these groups PSL2 of Q, where Q is a power of 2. And all of these examples have 3 orbits of vertices, 3 orbits of edges, and 1 free orbit of 2 cells. So the stabilizers for the orbits of vertices and edges are specified here. There is a lot of freedom in how to construct this, because first we must decide how to attach the one cells, the orbits of one cells, and then there is a lot of freedom in choosing how to attach the orbit of two cells, because we have to choose an element in a free group of high rank. So there are many ways to do this. For the others, the other families in the classification, there are also sets of examples which are similar. And well, now we define the Oliver and Segev graph as follows. It is the one skeleton of any two-dimensional fixed point free acyclic G complex of the type constructed in these examples. So we also consider a modification of this graph, which is obtained by attaching K-free orbits of one cells. Again, there are many ways to attach these free orbits. And well, now there are many ways to do this, but essentially there is just one way to do this, because these graphs are unique up to G homotopy equivalence. So now the second reduction is the following. If G is one of the groups in theorem A, and X is a fixed point free two-dimensional finite acyclic G complex, then we can modify this complex X to obtain a complex X prime, which is also a fixed point free two-dimensional finite acyclic G complex, and is obtained from this graph here by attaching K+1 free orbits of two cells. Moreover, we have an epimorphism of the fundamental group of X onto the fundamental group of X prime. So since we wanted to represent this group, it is enough to represent this group in a non-trivial way. So now we must prove that for each of these complexes which are obtained from this graph by attaching K+1 free orbits of two cells, there is a non-trivial representation in a unitary group. And we must do this for all of the groups in the classification and for each value of K which is greater or equal than 0. So now to do this, we want to understand the fundamental group of these examples, and there is a problem with doing this because there is no base point which is fixed by the action of G. And a way to handle this fundamental group is to use Basser theory. So if X is a G complex, we can consider this group extension of G by the fundamental group of X, which is obtained by lifting all of these homeomorphisms to the universal covering space X tilde of X. And when X is a graph, we have this extension, which is described by means of Basser theory. So Basser theory describes this as an amalgamated product, and also describes those maps here. And moreover, since we are interested in what happens when we attach orbits of two cells to this, well, there is a result by Ken Brown, which is the following. If X is obtained from a G graph by attaching R orbits of two cells along certain closed edge paths, all based at B0, then we have a group extension like this, where gamma is this group gamma here. These elements are obtained applying this map to these loops here. And these maps I bar and phi bar are obtained by passing to the quotient these maps. So if we understand this group, then we take a quotient by certain elements and we understand the extension of this by this. So now, since we want a representation of this group, well, it is enough to obtain a representation of this group gamma, which factors through this map here and does not factor through phi. Because if it factors through phi, then we obtain the trivial representation of the fundamental group of X. Well, so now to do this, we used a method which is inspired by a method that Jim Howie used to prove the Scott-Beagold conjecture. So the Scott-Beagold conjecture is the following statement. If we take a free product of 3 non-trivial finite cyclic groups, and we mod out by one word, then the group that we obtain is non-trivial. So to prove this, how we consider a subset of this product of 3 copies of SO3, where which is given by the elements whose first coordinate is a rotation of order L, the second coordinate a rotation of order M, and the third coordinate a rotation of order N. So each point in this space gives a non-trivial representation of this free product on SO3, because we simply send a generator of each of these cyclic groups to the corresponding rotations. And well, this space is homeomorphic to this product of copies of S2, and how we use the degree argument to prove that for some point here, the corresponding representation sends W to 1. So this representation passes to the quotient and gives a non-trivial representation of this group. And if we have a non-trivial representation, the group must be non-trivial. So we want to do something. We wanted to do something similar to this, and well, the method is the following. We first consider the extension gamma of the fundamental group of X1 by G, and we consider words here. So we want to obtain a representation of gamma which factors through this map here and does not factor through phi. So to do this, first we choose a Lie group G and the representation rho 0 of G in G. And then we want to twist this, which is a representation of gamma in the Lie group G, to obtain many representations of the group gamma. By moduli, we simply mean that M bar is a differentiable manifold, and that these representations vary differentiably. I will explain what that means, but it's not a moduli in the sense of algebraic geometry. And well, this compatibility between closed representations is the following. Each word W in gamma must induce a differentiable map from M bar to G simply by evaluating the representation on this word. So if we have this, then with some luck, we can prove that there is just one point on M bar such that the corresponding representation factors through phi. Recall that we do not want this to happen, but if there is a unique point with that property, we can control that. And well, then we can consider this map here, whose coordinates are the maps induced by these words Wi. And if we have some luck, M bar and this power of G are orientable and connected manifolds of the same dimension. So if we have this, we can consider the degree of this map W bar, and maybe we can prove that one bar is a regular point of this map and that this map has degree 0. If we can do this, since the degree can be computed as the number of preimages of a regular value, then we conclude that there is another point, tau bar, different from this unique point here, such that the image of this point by this map is this point. So if this happens, well, we can produce the desired representation of gamma, which yields the desired representation of the fundamental group of X on G. So this is the method, and now I will explain the construction of M bar, or sketch the construction. Well, Basser theory describes gamma as a quotient of this coproduct of a free group on these generators and these stabilizers here by certain relations which amalgamate some of these groups. Here, B and D are representatives of the orbits of edges and vertices of the graph X1. And well, then all of these representations are constructed by twisting phi composed with rho 0. So this map phi is simply the coproduct of these inclusions here and certain maps which send these generators to elements in G. So we understand this map. Well, it's obtained by passing to the quotient to that map. So we may twist this map in a certain way, and to do this, we define this space M, which is a product of certain centralizers in the Lie group of the images of these stabilizers by rho 0. So to each point here in M, we can associate a representation, which is obtained by conjugating the coordinates here of an element in gamma by different words involving the coordinates of M. So in this way, we obtain this moduli, and this has a problem, which is the following. Different points in M may yield the same representation, the exact same representation, and we do not want that to happen. So how we can solve this? Well, we can consider this group H, which is again a product of centralizers, but this time of the stabilizers of certain vertices, of all vertices in B except from one base point. And then we can consider an action of H on this moduli M. This action is cool, and we can define M bar as the quotient. And all of this structure passes to M bar. And well, finally, with some care, all of the steps in the method can be carried out in all of the cases that we need to consider. And well, a final remark, we choose G as the unitary group because centralizers in unitary groups are connected. And this simplifies a lot of things to obtain homotopies and in general in the argument. So this is all I wanted to say. These are the references, and well, thank you.
Well, thanks very much for your talk. There's plenty of time for questions, so please, does anyone want to comment something or ask a question?
I'll ask a question to break the ice. Hi, Ivan. Thanks for your talk. My question has to do with, maybe I missed this during the talk, like how exactly is the result that you've shown related to the conjecture? I understand that you solve it, but maybe you want to emphasize that.
Yes, it implies the conjecture. So this part is the conjecture, and it follows from this part.
Okay.
Really, the original conjecture by Casacuerta and Dix is for not necessarily finite two complexes. So it implies the finite case of the conjecture and the question by Aschbacher and Segev. I don't know how to pass from the finite case to the general case.
Okay, great. Thanks a lot.
One question, Ivan. So the non-finite case, is it believed to be true, or I mean, are there any results?
I think that it is believed to be true, yes. With geometric hypothesis on the space, it holds. For example, if the space is cut zero or collapsible. But I don't know how to pass from one case to the other, because if the space is not compact, there may not be a compact subcomplex which is fixed by the action of chi, or stable by this action. So I don't know.
Thank you.
Any other question or comment? Otherwise, let's thank the speaker again and take a minute before the next talk.